Now we're going to talk about section 11.4, which is the equations of simple harmonic motion. I've been ranting about a spring mass system where the mass goes back and forth. Let me write this out so we have something to look at. But now we're going to talk about the equations describing the motion. So an equation describing the displacement as a function of time, the velocity, and the acceleration. So I'm going to abbreviate this and just say SHM for simple harmonic motion. So what we want to think about in this case, and there's a really nice argument in this section of the book that elaborates on simple harmonic motion, and it begins by considering the x-coordinate of a particle on a rotating turntable. So it's a bit involved. It's worth looking at. I'm going to skim over the top, details of this derivation, and I'm going to focus on the results that we get out of it. So consider this. I have a turntable of radius A. So consider this circle here. And this here is going to be my x-axis next to it. So consider a particle that's on this turntable. And remember, it's got a radius of A. Well, if I look at the x-coordinate of this particle, I notice that it's going to go to a farthest point like this. Maybe I should start by saying x equals 0 here on a line that goes from our x-axis through the center of that turntable. But the maximum x value that that particle will have as it goes around, remember this turntable is rotating. At some point, it's going to have some angle phi that that particle makes on the turntable with this horizontal line. But anyway, that particle will be moving back and forth in this x direction. So as the turntable turns and this thing moves in this direction, the maximum displacement that it will have will be the radius of that turntable in the x direction. And the minimum displacement it has, or the farthest left it'll get on the x-axis, is minus a. So you have this particle right here on the edge of a turntable just going round and round and round. We're going to say this, that angle phi, if this thing rotates at a constant rate, there's going to be a linear relationship between that angular displacement phi and the time. And it's going to be omega t, where omega is the angular velocity that we mentioned in the last section. So this is omega, the angular velocity. All right, now A, sorry, I want to write x. Let me erase that real quick here. If I want to know what the x coordinate is, notice that I have a radius vector of length a, and it makes an angle of phi with the x direction, or with the horizontal. So that if you'll remember what happened in 131, where you looked at basic vector mechanics and triangles and trig, x is going to be equal to a cosine of that angle phi. I feel compelled to draw a little triangle over this and say, this is a, and at any given instant, that particle has an x coordinate here and a y coordinate here, and I form this little y triangle. So because of that little triangle formed by that position of that particle, that's why I can write x equals a cosine of phi. Now, remember from our definition of omega that at one point we said omega equals 2 pi f equals 2 pi over the period. Therefore, I can write out omega. Actually, there's no therefore. I'm just going to write it one more time. But I just want to remind us that we looked at this definition of omega, that angular frequency, angular velocity in terms of a frequency. So knowing that, I can plug that into this expression for phi and write that x must be equal to a cosine of omega t. But remember, omega is 2 pi f, so that I can write out a cosine 2 pi f times t like that. Anyway, I have, when I'm looking at this circular motion, I have that my x position is very simply expressed as a cosine function. Really, this is why we're calling this simple harmonic motion. Simple harmonic motion implies that an equation describing a position or velocity is going to be a trigonometric function, either sine or cosine. So that gives us our position. I'm going to come back to this, but I need to go to a new page because having this, this x coordinate, I want to look at my my x coordinate and looking at position. I want to talk about my velocity in the x direction. And so remember the velocity of a particle. So I'm going to write the speed or the velocity of a particle that's undergoing uniform circular motion. It's a good thing I'm saying this because I'm not sure that it's actually legible, but in uniform circular motion, and I just consider one part of this particle's little motion here. It's going to be a distance a out. If this instance in time, it makes the position vector of that particle makes an angle phi with a horizontal. But notice its velocity is perpendicular to that radius vector formed by A. And we remember that V is going to be equal to omega times R, if R is the radius of a circle. So for us, we're going to write that velocity is going to be equal to omega times A, which is equal to 2 pi f times A, like that. But from diagram, we're going to see a relation for V sub x. And I'm going to write this, that V sub x, and I need to do one thing quickly here. I'm going to draw a vertical line here. I'm going to point out that the angle that velocity vector makes with that vertical line, that angle that it makes is going to be phi. It's that exact same phi. You have to move this little particle around on that circle to convince yourself that those angles are the same. But when I do that, what this little thing here is going to form is another right triangle where this is V, and I have a little right triangle. Notice this little vector here, this opposite side from that phi, this little side here, that is the x component of my velocity. And you'll notice that from that right triangle, the opposite side from phi is V sub x. The hypotenuse is going to be V. So V sub x is going to be equal to sine of phi. But you'll also notice when you look at this, I'm sorry, it's going to be V times sine of phi to be totally complete. But you'll also notice that when phi is, say, like 10 degrees, that x component of the velocity is negative, so a negative sign needs to come out in front of that. But we've just written down what V is in terms of 2 pi f times A. So if I replace that there, I have minus 2 pi f times A, that's for the V component, and then, or for the V factor. Then I have sine of phi, but that is equal to 2 pi f times t. Now that's starting to look like a pretty complex function, but if I come back and remember that omega equals 2 pi f, then I can replace these 2 pi f terms here, and I can write this, that V sub x equals minus omega times A sine omega t. Now I'm not done with that expression yet, but this is going to give me the x component of my velocity. This is a subtle thing, the results are going to be important for this, but if you don't understand what I'm doing here, it's worth looking this over, then going back in the book and following their argument through, because it's leading to a nice, interesting result. Just bear with me for one more quantity. So if this is, we did position, and now we did velocity. If you'll remember from 131, there's one remaining quantity of motion that we care about, which is the acceleration. In uniform circular motion, you'll remember that if something moves on a circle with constant speed, its acceleration is always towards the center of that circle. It has that centripetal acceleration. So now I'm going to draw my little turntable again, and I'm going to put my particle, that same little angle phi here like that, point out that I have this velocity that's tangential to that radius vector, that position. And then I'm going to point out that there is an acceleration. And I suppose I should write a sub rad. That's unreadable, but here, let me write it out. But I'm going to write a sub rad. And if you remember from 131, normally we would say that radial acceleration or that centripetal acceleration was v squared over r. But when we considered this omega, this angular velocity, it also allowed us to write omega squared times r. And in our case, remember that omega is 2 pi f, so that's just 4 pi squared f squared when you plug in 2 pi f and square it. And r is just equal to a, like that. So that's your radial acceleration. And you'll notice that if I draw out that radial acceleration like this, it makes an angle phi with a horizontal. You can convince yourself by looking at these diagrams that that is that angle. And if I do that, I form a little right triangle. Notice that this side here, right here, that's going to be the x component of my radial acceleration. And I'm going to say a sub x is just equal to minus a rad cosine phi. I write cosine phi because I'm looking for that component of that radial acceleration. And I'm using a negative sign there because I noticed that when, let's say phi again is 10 degrees, just looking at this little drawing here, that acceleration, the x component, is directed towards the left. It's in the negative direction. So what I want to do after having written that out is I have that expression for a rad. I'm going to write minus 4 pi squared f squared a, and cosine of 2 pi f times t again. But remember, maybe this didn't need to be done in this one extra step, but remember that 2 pi f is equal to omega. So it allows me to write simply for a sub x minus omega squared a cosine of omega t. Now I wrote out all this stuff. Oh, and this is the acceleration in the x direction, okay? Now I started with the displacement. And what I wrote initially was this, that x was equal to a cosine omega t. And so what you'll notice is from these two expressions that cosine omega t part, well, the a cosine omega t part, that's just x. I can rewrite a sub x as a sub x is equal to, and let me make sure that doesn't look like a negative sign there. I can write a sub x equals minus omega squared x, like that. What's awesome here is that the motion is, well, the acceleration is proportional to x. So I would write a sub x is proportional to x, where alpha is my little symbol that means proportional to. Now what the book is arguing and what I'm trying to say here is that because of this expression, because acceleration is proportional to the displacement, that particle, when you just look at the particle in the turntable, when you just look at the x component of its motion, it's doing simple harmonic motion. So I'm going to write out finally in x, this is simple harmonic motion. And what's interesting here is we got all these equations that we didn't have before. You know, it would take calculus to derive equations for the displacement as a function of time and the acceleration velocity as a function of time in the case of that mass going back and forth with a spring. But here, by looking at this turntable, we came about with this nice application of these sine functions to the motion. Now, writing this out one more time, I'm going to write a sub x equals minus omega squared x for mass spring system. And I'll spare you me drawing that one more time. We had originally an expression that a sub x was equal to minus k over m times x. I lied, I can't resist it. I have to draw this stupid thing, x equals 0. So that acceleration is proportional to minus k over m times x. When I compare these two equations, I see that omega squared is equal to k over m. Now remember what omega is. Omega is the angular frequency, but that's related to the frequency and the period. This expression we have now allows us to write omega equals the square root of k over m, which is an important equation for us. Remembering that the frequency is equal to omega over 2 pi. Really, I kept saying omega was equal to 2 pi f. This allows me to write, oh, the frequency is just equal to 1 over 2 pi times omega, which is the square root of k over m. So if you know what k is, that spring constant, how stiff that spring is, and how big that mass is, you can see what the frequency of motion is going to be here. You just take k divided by m, take the square root, and do this 1 over 2 pi. And because the period of motion is equal to 1 over f, you can just take that last expression for f and write the period is equal to 2 pi times the square root of m over k. It's interesting. You can look at this mass moving back and forth up here with that spring, and you can see that from this expression, the time it takes to complete a cycle to go back and forth one time, it's proportional to the square root of m. As m gets bigger and bigger, as the mass gets bigger, this thing takes a longer period of time to go back and forth once. And so the equation that we've derived here, this expression for that period, makes fundamental physical sense. I'll leave that there and encourage you to go look in the book, if not to understand the whole thing, just to make sure you know where these equations are and make sure that you understand from the examples in the book how each one is applied to this motion.